big is the universe? BBC has an amazing explanation that will definitely make us feel so tiny we're insignificant. For all our might and abilities, humans are really puny creatures. The universe we exist in is just too vast and beyond our intuitive contemplation. As we start the new year with wishes and resolutions, here is a size comparison of our Earth to everything else in the universe. It should help us remember just how insignificant we truly are, contrary to what we feel like. Let us go rambling about the universe. This is the invitation that American astronomer Harrow Shapley gave an audience in Washington, D.C. in 1920. He was taking part in the so-called Great Debate with fellow scientist Heber Curtis on the scale of the universe. Shapley believed that our Milky Way galaxy was 300,000 light years across. That is actually 3 times too big, according to the latest thinking, but his measurements were pretty good for the time. In particular, he calculated broadly correct proportional distances within the Milky Way, the position of our sun relative to the center of the galaxy, for instance. In the early 20th century, though, 300,000 light years seemed too many of Shapley's contemporaries, an almost absurdly large figure. And the idea that other Milky Way-like spiral galaxies, which could be seen with telescopes, were equally large was outlandish. Indeed, Shapley himself believed the Milky Way must be exceptional. Even if the spirals are stellar, they are not comparable in size with our stellar system, he told his listeners. Curtis disagreed. He thought correctly that there were many other galaxies as big as our own spread throughout the universe. But, interestingly, his starting point was a belief that the Milky Way was far smaller than Shapley had calculated. According to the calculations that Curtis used, the Milky Way was just 30,000 light years in diameter, or about 3 times too small going on modern measurements. 3 times too big, 3 times too small. When we are talking about such enormous distances, it is understandable that astronomers debating almost a century ago could get their figures a little bit wrong. Today, we are fairly confident that the Milky Way is probably between 100,000 and 150,000 light years across. The observable universe is, of course, much larger. According to current thinking, it is about 93 billion light years in diameter. How can we be so sure? And how did we ever come up with such measurements from right here on Earth? Ever since Copernicus argued that the Earth was not the center of the solar system, it seemed that we have always found it difficult to rewrite our preconceptions of what the universe is, especially how big it may be. Even today, as we will see, we are gathering new evidence to suggest the whole universe may be much bigger than some have recently thought. Caitlin Casey, an astronomer at the University of Texas at Austin, studies the universe as we know it. As she points out, astronomers have developed an ingenious array of tools and measuring systems to calculate not just the distance from Earth to other bodies of the solar system, but the spans between galaxies and the journey to the edge of the observable universe itself. The steps to measure all these things are known as the cosmic distance ladder. The first rung of the ladder is easy enough for us to get onto, and these days it relies on modern technology. We can just bounce radio waves off of neighboring planets in the solar system, like Venus and Mars, and measure the time it takes for those waves to come back to Earth, says Casey. That gives us a very precise measurement. Big radio telescopes like Arecibo in Puerto Rico can do this sort of work, but they can also do even more than that. Arecibo, for instance, can detect asteroids flying around the solar system and even produce images of them based on how radio waves reflect off the asteroid's surface. But using radio waves to measure distances beyond our solar system is not practical. The next rung on the cosmic distance ladder is something known as parallax measurement. This is also something we do all the time without realizing it. Humans, like many animals, intuitively recognize the distance between themselves and objects, thanks to the fact that we have 2 eyes. If you hold an object in front of you, say your hand, and look at it with one eye open, then switch to using only the other eye, you will see your hand appears to shift sideways slightly. The difference between those 2 observations can be used to work out the distance to the object in question. Our brains do it naturally, with the information from both our eyes. And astronomers do the same thing with nearby stars, except they use different sensors, telescopes. Imagine having two eyes floating in space, either side of our sun. Thanks to the Earth's orbit, that is exactly what we do have. And we can view stars shift relative to objects in the background by this method. We take a measurement of where stars are in the sky, say in January, and we wait 6 months and measure those same stars in July when we're on the opposite side of the sun, says Casey. However, there is a point at which objects are so far away, about 100 light years, that the observed shift is too small to provide a useful calculation. At this distance, we are still nowhere near the edge of our own galaxy. The next step up is a technique called main sequence fitting. It relies on our knowledge of how stars of a certain size, known as main sequence stars, evolve over time. For one thing, they change color, gradually becoming redder with age. By measuring their color and brightness accurately, and then comparing this to what is known about the distance of closer main sequence stars measurable by parallax, we can estimate the positions of these more distant stars. The principle that backs these calculations is that which states that stars of the same mass and age would appear equally bright were they the same distance from us. Since they are often not, we can use the distance in those measurements to work out how far away they actually are. Main sequence stars, when used for this analysis, are considered one type of standard candle, meaning a body whose magnitude or brightness we can calculate mathematically. These candles are dotted around space, lighting the universe in predictable ways. But the main sequence stars are not the only examples. This understanding of how brightness relates to distance is pretty fundamental to working out the distance to even farther objects, like stars in other galaxies. Main sequence fitting will not work there, though, because the light from those stars, which are millions of light years away if not more, are hard to analyze with accuracy. But way back in 1908, a scientist called Henrietta Swan-Leavitt at Harvard came up with a fantastic discovery that has helped us measure such colossal distances. Swan-Leavitt realized that there was a special class of stars called cepheid variables. She made this observation that a certain type of star varies its brightness over time, and the variation in the brightness, the pulsations of these stars, relates directly to how bright they are intrinsical, says Casey. In other words, a brighter cepheid will pulsate more slowly, over the course of many days in fact, than a dimmer cepheid. Because astronomers can measure the pulse of a cepheid relatively easy, they can predict how bright the star is. Then, by observing how bright it actually appears to us, they can calculate its distance. This is similar in principle to the main sequence fitting approach, in that brightness is again the key. But the key point is that distance can be measured in different ways. And the more ways of measuring distances we have, the better we can understand the true scale of our cosmic backyard. It was the detection of such stars in our own galaxy that convinced Harlow Shapley of its great size. In the early 1920s, Edwin Hubble detected cepheid variables in the nearby Andromeda galaxy and discerned that it was just under 1 million light years away. Today, our best estimate is that the galaxy is actually 2.54 million light years away. But that does not shame Hubble's measurement. In fact, we are still trying to work out the best estimate for the distance to Andromeda. The 2.54 million light years figure is actually an average of several recent calculations. This is the point at which the sheer scale of the universe even now continues to boggle our minds. We can make very good estimates, but in truth, it is extremely difficult to measure distances between galaxies with fine accuracy. The universe really is that big, and it does not stop there. Hubble also measured the brightness of exploding white dwarf stars, type 1a supernovas. These can be seen in quite distant galaxies, billions of light years away. Because the brightness of these explosions is calculable, we can determine how far away they are, just like we can with cepheid variables. The type 1a supernovas and cepheid variables then are both additional examples of what astronomers call standard candles. But there is one more feature of the universe that can help us to measure really extreme distances. It's called redshift. If an ambulance or police car blaring a siren has ever passed you in the street, you will be familiar with the Doppler effect. As the ambulance approaches you, the siren seems high in pitch, and then, as it passes you and moves away, it falls again. The same thing happens with light waves, on a much finer scale. We can detect the change by analyzing the spectrum of light from distant bodies. This spectrum will have dark lines in it because some specific colors are absorbed by elements in and around the light source, the surface of stars, for example. The further away objects are from us, the further towards the red end of the spectrum those lines will be shifted. That is not just because the objects are far away, but because they are actually moving further away from us over time, thanks to the universe's expansion. And seeing redshift in the light from distant galaxies is one way of proving that the universe is indeed expanding. It is like putting dots on the surface of a balloon, each representing a galaxy, and then blowing up the balloon, says Kartik Sheth, a program scientist at NASA. As the balloon expands, the distance between the dots on its surface grows. As the universe is expanding, each galaxy is moving away from the others. Basically, a wave would normally just be whatever frequency it was emitted at, but now you're stretching space-time itself, so therefore the wave looks longer. The faster the galaxy is moving from us, the further away it must be, and the more redshifted its light will be when we analyze it back here on Earth. Again, it was Edwin Hubble who discovered that there was a proportional relationship between the cepheids in distant galaxies and how much the light from those galaxies was redshifted. Now comes the big key to our puzzle. The most redshifted light we can detect in the observable universe suggests that light has reached us from galaxies that are 13.8 billion years old. Because this is the oldest light we have detected, that also gives us a measurement for the age of the universe itself. But over the last 13.8 billion years, the universe has been continually expanding, and at first it did so very rapidly. Taking that into account, astronomers have worked out that the galaxies right on the edge of the observable universe, whose light has taken 13.8 billion years to reach us, must now be 46.5 billion light years away. That is our best measurement for the radius of observable universe. Doubling it, of course, gives the diameter 93 billion light years. This figure rests on many other measurements and bits of science, and the culmination of centuries of work. But as Casey notes, it's still a little rough. For one thing, given the complexity of some of the oldest galaxies we can detect, it is not clear how they were able to form so quickly after the Big Bang. One possibility is that somewhere, a few of our calculations are not quite right. If one of the rungs of the cosmic distance ladder is off by 10%, then everything's off by 10%, because they rely on each other, says Casey. And where things get really complex is when we try to think about the universe beyond that which is observable, the whole universe, as it were. Depending on which theory of the shape of the universe you prefer, the whole universe could actually be finite or infinite. Recently, Miran Vardanyan and colleagues at the University of Oxford in the UK analyzed known data about objects in the observable universe to see if they could work out anything about the shape of the whole universe. The result, after using computer algorithms to look for meaningful patterns in the data, was a new estimate. The whole universe is at least 250 times as large as the observable universe. We can never see these more distant regions. Still, the observable universe alone should be big enough for most people. Indeed, for scientists like Casey and Sheth, it remains a constant source of fascination. Everything that we've learned about the universe, how big it is, all the amazing objects that are in it, we do that simply by collecting these photons of light that have traveled millions and millions of light years only to come back and die on our detectors, our cameras, or radio telescopes, says Sheth. It's rather humbling, says Casey. Astronomy has taught us that we're not the center of the universe. We're not even at the center of our solar system or at the center of our galaxy. One day we might travel physically much further into the universe around us than we have so far dreamed. For now, we can only look. But just looking can let us ramble pretty far. To you and I, the Earth might seem like a large place, but in astronomical terms, our planet is actually quite small. Comparatively, the gas giant planets in our solar system are significantly larger. Jupiter's Great Red Spot alone is larger than the entire North American landmass, and at least 6 Earths could fit across Saturn's planetary rings. Planets aside, Earth pales in comparison to the size of the Sun. Astronomers estimate that approximately 1.3 million Earths would fit inside of the Sun, and it's considered to be on the small side when compared to other stars found in the Milky Way galaxy. Even if that didn't underscore the Earth's insignificance, keep in mind that our solar system is an insignificant blip inside the Milky Way galaxy. Furthermore, the Milky Way is an insignificant blip in the Laniakea supercluster, which is also an insignificant blip compared to the rest of the universe.